Hello everyone, my name is Neha. I am a student of BSc Chemistry Honors second semester and I am here for explaining the topic chemical kinetics from physical chemistry. So chemical kinetics is that branch of physical chemistry which deals with the study of rate of reaction, factors affecting or that govern these rates and the mechanism by which the reactions proceed. So, rate of reaction refers to the speed with which the reaction takes place. For example, some reactions are instantaneous, will take place in milliseconds. Some reactions are of measurable speeds, like some seconds or minutes, and some take very long duration, that is hours, or it may take years, like that in the case of rusting of iron. In terms of physical chemistry, we can explain rate of reaction as the rate of change of concentration per unit time. That is, we can say that R is equals to dx upon dt, where dx is a small change in the concentration of the reactant during the reaction and dt is that small interval of time during which that small change in concentration occurs. Now let us study about the factors affecting the rate of reaction. So first of all, nature of reactants. Affects the rate of reaction. Reactants, temperature of the system, nature of solvent, presence of catalyst, presence of any kind of light or radiation such as sunlight or any other kind of radiation, concentration of reactants, and pressure of the system. Now, let's express the rate of a particular reaction. Suppose A moles of a reactant A and small b moles of a reactant B give some product. So, according to the rate law, its rate of reaction can be expressed as K into the concentration of A raised to the power small a into capital B raised to the power small b, that is the stoichiometric coefficients of the reactants raised to their respective concentration. And here K is the specific reaction rate. This is also known as rate constant. Now from this rate of reaction, we can determine the order of the reaction, which is small a plus b, that is sum of the powers of the concentration of the reactants in the rate law of a particular reaction. Now let's start with the derivation of zero order rate constant, that is expression for the rate constant for a reaction of zero order. Let us take a reaction in which a reactant gives some products. Now we can express the rate of this reaction as the change, or we can say that as the decrement in the concentration of A with respect to time, which can be written as minus d by dt of concentration of A, or we can also write it as K into A raised to the power 0, that is, for zero order it does not depend upon the concentration of the reactants, which comes out to be K. So here we can say that minus dA is equals to kdt. Now integrating both sides, we get this side A and this side minus kt plus integration constant C. Let us say C. Now A plus kt is equals to C. At T is equals to 0, the concentration of the reactant is maximum. Let us represent it with the notation A naught. Now putting these values in the equation first, we get A naught plus K, replacing T with 0, is equals to C, which is our integration constant. So here we get that A naught is equals to C. Putting this value from equation 2 in equation 1, we get by 1 and 2, we get A plus KT is equals to A naught. By further transformation, we get A minus A naught is equals to KT. Here, taking negative sign common, we get A naught minus A is equals to KT. Here, A naught is the initial concentration, which is the maximum one. A is the concentration at the particular time t we are calculating the rate, and K is the rate constant or the specific rate, reaction rate. Now by Doing furthermore changes, we can get the reactions rate constant to be A naught minus A divided by T. This is the expression for the rate constant for a reaction of zero order. Now if we plot a graph and observe the characteristics of reactions of zero order, it is found that when we plot a graph against concentration and time, we get a slope like this. And here the concentration is of reactants, that is A. Here we have taken and represented it with the letter A. This decrement in the slope of the graph denotes that at the initial phase of the reaction, the concentration of reactants was the maximum, and as the reaction proceeds, the concentration of reactions keep on decreasing and the concentration of product keep on increasing. And if we plot a graph of rate against the concentration, we found it to be constant, which again denotes that in zero order the rate is independent of the concentration of the reactants. So now let's calculate the half-life period for the zero order. Half-life period is that time in which half of the concentration, half of the amount of the reactants is consumed. Half of the reactant amount is consumed. For example, here we can denote T is equals to T half, which denotes half-life period. In this case, the concentration of the reactant would be the half of the initial concentration, that is here A naught divided by 2. As we know, the expression for the time period is 1 by K concentration of A naught minus concentration of A. Here T is equals to T half 1 by K A naught as it is. We will replace A naught by 2 at the place of A. Here we get T half to be A naught divided by 2K. So this is the expression for determining the half-life period for zero order. In this it is clearly seen that the half-life period is, so here we can clearly see that the half-time period or half-life period is directly proportional to the initial concentration of the reactants in the case of zero order. Now let's take a quick glance at the rate at the reactions of first order, and let us determine the expression for the rate constant for a reaction of first order. So in first order, we can say that let us take a reactant, again A reactant, which gives some products, right? Now as the reaction is of first order, so the rate of reaction, let us denote it with ROR. that is directly proportional to the concentration of reactant raised to the power 1, as it is the first order. Now, let us suppose that at time t, the concentration of the reactants from A decreased to, let us assume that this at time t, at t is equals to 0, the concentration of the reactant is small a and the product is 0. At t is equals to at a particular time, the concentration of the reactant decrease and become A minus X, which gives X moles of product. Let's see. Now, as we can say that rate of reaction is directly proportional to the concentration of the reactant, so dx by dt is directly proportional to A minus X. Let us write it in this form: dx is equals to dx by dt is equals to k into A minus X. Now, simplifying this equation further, we get dx upon A minus X is equals to k dt. Now, integrating both sides, we get minus of ln A minus X is equals to kt plus c. Here c is again integration constant. Now, taking the special case when at t is equals to 0 and a is equals to and x is equals to 0, that is when no product is formed. So in this case, we can put these values in the first equation number 1 obtained above, and we will get minus ln a minus 0 is equals to k into t is equals to 0, t value is 0, so k into 0 plus c. So from here we can get easily the value of c, that is the integration constant, which came out to be minus ln of a is equals to c. Putting this value from equation 2 in 1, we get by 1 and 2 we get minus ln of a minus x is equals to kt minus ln of a, which gives us, on further simplification, it gives us ln a minus ln a minus x is equals to kt. This further gives us the value of rate constant is equals to ln a minus ln a minus x upon t. Now, as we know that ln can be replaced with 2.303 log base e. So, by replacing this, we can get the equation as 2.303 log A minus log A minus x upon t. Now applying the identity of log A minus log B is equals to log A upon B, we can say K is equals to 2.303 log 2.303 upon T. So we get K is equals to 2.303 upon T log A upon A minus X. Here A is the initial concentration of the reactant and A minus X is the concentration of the reactant at time t, and K is the rate constant. Now let us determine the graphical relation for first order. If we plot a graph against log Ct is the concentration of the reactant. Here we are denoting Ct with the reaction with the concentration of the reactant at time t, and on the x-axis let us denote time. So we got this kind of slope. Here we have replaced Ct, or we can say it A minus x, as we have discussed earlier. Taking this as we have derived whole expression of rate constant, so we can use this term, either this term or this term. Now let us determine the half life period for first order. That is T is equals to T half, concentration that is A is A by 2. That is where X is A by 2. That is the concentration of the reactant at time t. Now putting the values in the equation, T is equals to 2.303 upon K log A upon A minus X. Here T is equals to T half is equals to 2.303 upon K log A upon A minus, replacing X with A by 2, which is the half concentration of the reactant as that of the initial. Half of that we can replace it. T half is equals to 2.303 upon K log A by 2, which on further simplification we get 2.303 upon K log 2. As we know, the value of log 2 is approx 0.3010, something like this. We can say that doing further calculations, putting the static value of log 2, we get T half is equals to 0.693 upon K.